Hello students, I hope you all have just gone through my previous videos, and today we are going to discuss the module 4. In that, the last part, that is part 4, with respect to visible surface detection methods for 6th semester in CG, that is Computer Graphics and Visualization for 17 series batch. Moving on to the contents, we would be having 4 topics here. First is the classification of visible surface detection algorithms, backface detection, depth buffer method, and some Opengl functions with respect to visibility detection of polygons. We can broadly classify visible surface detection algorithms according to whether they deal with the object definitions or with their projected images. So we can classify them object space methods, image space methods. Although there are major differences in the basic approaches taken by the various visible surface detection algorithms, such as sorting and coherence methods for improving performance. Sorting is used to facilitate our depth comparisons by ordering the individual surfaces in a scene according to their distance from the view plane, whereas coherence methods are used to take advantage of regularities in a scene. Backface detection, where we can simplify the backface test by considering the direction of the normal vector n for a polygon surface. If v is a view which is a vector in the viewing direction from our camera position, which is shown in the figure, you can see that is we are seeing this pyramid, but what we can see with respect to ABC is only the triangular part of that particular pyramid, that is a polygon. So what view we would be getting is the viewport as shown in the figure, which gives you the back face of V view where n is greater than 0. With respect to a right-handed viewing system with the viewing direction along the negative ZV axis as shown in the figure here, where we are viewing with respect to the Z axis, you can say a polygon is a backface if the Z component C of its normal vector n, which satisfies the condition C is less than 0. Also, we cannot see any face whose normal has Z component C is equal to 0 because our viewing directions is grazing that polygon. Which polygon we are grazing here? We are just grazing the triangle polygon. Thus, in general, we can label any polygon as a backface if its normal vector has a Z component value which satisfies the inequality, that is C is less than or equal to 0. Similar methods can be used in packages that employ a left-handed viewing system, as we saw in the previous right-handed system. In these packages, plane parameters A, B, C, and D can be calculated from polygon vertex coordinates specified in a clockwise direction. Inequality then remains a valid test for points behind the polygon by examining parameter C for the different plane surfaces describing an object. We can immediately identify all the back faces. For considering the object, this object, like as example, where more tests must be carried out to determine whether there are additional faces that are totally or partially obscured by other faces. In general, backface removal can be expected to eliminate about half of the polygon surfaces in a scene from further visibility tests. Coming to the topic depth buffer method, a commonly used image space approach for detecting visible surface is the depth buffer method, which compares surface depth values throughout a scene for each pixel position on the projection plane. As shown in the figure below, here these surfaces overlapping pixel position x, y on the view plane. The visible surface S1 has the smallest depth value. As each surface is processed, which can be processed in any order, its depth from the view plane is compared to previously processed surfaces. These surfaces can be processed in any order. If a surface is closer than any previously processed surfaces, its surface color is calculated and saved along with its depth. The visible surfaces in a scene are represented by the set of surface colors that have been saved after all surface processing is completed. As simplified by the name of this method, two buffer areas are required. A depth buffer is used to store depth values for each x, y position as surfaces are processed, and the frame buffer stores the surface color values for each pixel positions. Going with the algorithm of depth buffer, here we can have two steps. First is the initialization of depth buffer and frame buffer, so that for all buffer positions x, y, depth buffer of x, y is equal to 1, that is 1.0 we have defined here. Frame buffer of x, y is equal to background color. Second step we can go in the algorithm is processing each polygon in a scene one at a time as follows. First one, for each projected x, y pixel position of a polygon, state the depth z, which is already unknown, which is already known. If z is less than depth buffer of x, y, compute the surface color at that position and set depth buffer of x, y is equal to z. Frame buffer of x, y is equal to surface color. After all surfaces have been processed, the depth buffer contains depth values for the visible surfaces and the frame buffer contains the corresponding color values for those surfaces. Given the depth values for the vertex position of any polygon in a scene, we can calculate the depth of any other point on the plane containing the polygon with respect to x, y. Thus, we can define z is equal to minus ax minus by minus d divided by c, where a, b, c, d are planes. If the depth of a position x, y has been determined to be z, then the depth z dash of the next position x plus 1, y along the scan line is obtained as z dash is equal to minus a of x plus 1 minus by minus d divided by c, where z dash can be once again given as z minus a divided by c. You can see these are the scan lines we were talking about. Y scan line, y minus 1 scan line, similarly x scan line, x dash scan line, and so on. Therefore, x dash can be defined as x minus 1 divided by m, where m is the slope of the edge. Therefore, z dash can be defined as z plus a divided by m plus b divided by c. If we are processing down a vertical edge, then z dash can be given as z plus b divided by c. One slight complication with this approach is that while pixel positions are at integer of x, y coordinates, the actual point of intersection of a scan line with the edge of a polygon may not be. As a result, it may be necessary to adjust the intersection point of rounding its fractional part up to or down, as it is done in scanline polygon fill algorithms. An alternative approach is to use a midpoint method or Bresenham's type algorithms for determining the starting x values along edges for each scan line. The method can be applied to curved surfaces by determining depth and color values at each surface projection point. In addition, the basic depth buffer algorithm often performs needless calculations. Objects are processed in an arbitrary order so that a color can be computed for a surface point that is later replaced by a closer surfaces. Let us discuss some of the OpenGL visibility detection functions as we have categorized them with respect to OpenGL polygon culling functions, where we are defining the backface removal with respect to GL enable GL underscore cull underscore face. So this is an function in OpenGL will be using to for the removal of backface, and GL cull face off mode, where parameter mode is assigned the values as GL underscore back, G underscore front, GL underscore front and back as the user need. By default, these parameter mode in the GL cull phase function has the value GL underscore back. The culling routine is turned off with GL disable. As we know, GL enable, GL disable can enable and disable any OpenGL functions in OpenGL. And next category we have is OpenGL depth buffer functions, where we are initializing the display mode, as we are using in most of the programs of our laboratory as well. Glut underscore single, glut underscore RGB, and glut underscore depth, where depth refers to the depth buffer values which can be initiated with respect to GL clear depth buffer bit, which sets depth buffer values to the maximum value with respect to 1.0 by default. And here this also we can enable it with respect to GL enable, and we can disable it with respect to GL disable. And GL glut underscore single is for the buffers, whether we are using single buffer or double buffer, and GL underscore RGB for the color model, whichever we are using, that is RGB color model we are using. GL color depth, where we are mentioning the maximum depth. The parameter maximum depth can be set to any value between 0 and 1, where projection coordinate in OpenGL are normalized to the range of -1 to 1, and the depth value between near and far clipping planes with respect to 0 and 1. Now then we have depth range function also in OpenGL with respect to normal depth, and normal depth with respect to near and far. By default, near normal depth is equal to 0 and far normal depth is equal to 1. So as the user needs. Another option available in OpenGL is the test condition, which is to be used to depth buffer routines such as GL depth function, where we are testing any condition with respect to GL underscore less, GL underscore greater, GL underscore equal, GL underscore not equal, GL underscore less than or equal, GL underscore greater than or equal, GL underscore never, that is no points are processed, and GL underscore always, that is default value we can give for parameter test condition is GL underscore less. We can also set the status of the depth buffer with respect to GL depth mask of write status, where we are giving it with respect to GL underscore true, which is a default value, and GL underscore false with respect to write mode for the depth buffer, which is disabled, and we can retrieve values only when the comparison is needed. Then OpenGL wireframe surface visibility methods, where we are defining polygon mode with respect to whether it is a front and back or front or back, and then GL underscore line, that is the primitive, we are defining it here, both with respect to displays. Then GL enable with respect to depth test, then polygon mode again with respect to color 3F, that is 3 values in float we are defining, polygon mode with respect to front, back, and GL fill for the polygon fill. GL enable polygon offset fill, that is the value we are, integer value we are providing here. Then polygon offset, color 3F, that is 0, 0, 0 means like all zeros we have given, so black color will be getting. Disable and enable of polygon offset fill. We have one more category in OpenGL, which is a depth queuing function, where we can vary the brightness of an object as a function and its distance from the viewing position. That is GL enable GL fog. GL enable fog a underscore mode, that is which mode it will be in, with respect to GL underscore linear. This applies linear depth function to object color using dmin, which is 0 by default, and dmax with respect to 1. But we can set different values for dmin and dmax with the following functions: GL underscore fog underscore start comma minimum depth, GL fog f of GL underscore fog underscore end comma maximum depth with respect to the user needs. In these two functions, parameters min depth and max depth are assigned floating point values, which are although they are integer values, which can be used if we change the function suffix to I. We can use the GL fog function to set an atmosphere color, that is to be combined with the color of an object after applying the linear depth queuing function. So these are some of the OpenGL functions for with respect to visible surfaces. And that's all about the last part of the fourth module. If you like the video, share it, subscribe it. Thank you.